a Portland Community College mathematics telecourse. A course in arithmetic review, produced at Portland Community College. With the exception of the location of the decimal point, division of decimals is the same as division of whole numbers. This really was the whole reason decimals were invented in the first place, to allow us to treat a special category of fractions as though they were whole numbers in operation. Let's begin with a special case, and that special case is this. Our divisor is a whole number, and a whole number, of course, means one where the decimal point is on the immediate right. Where the decimal point is in the dividend makes no difference. If the divisor is a whole number, the decimal point simply goes straight up into the quotient. Once you have located the decimal point, simply divide 176 by 32 as though that decimal point was not there. Now placement here is very important. 32 goes into 1 0 times. 32 goes into 17 0 times. And those zeros, particularly this one, is all important. Then 32 goes into 176 about 5 times. 5 times 32 is 160. Subtract, we get 6, 1. Now, behind the decimal point on the end, we may, again, insert as many zeros as we need or want without changing the value of the number. So now bringing down the next digit, which is 0. 32 goes into 160 5 times. 5 times 32 is 160. And we're done. So, if you're dividing by a whole number, the decimal point of the dividend goes straight up. Then divide the number exactly as you would whole numbers, remembering that behind the decimal point, on the end, you can insert as many extra zeros as you need. Then you divide until either it comes out evenly, as it did here, or until some aspect of the problem dictates that you stop at a certain place. Let's reverbalize that for our notes. If the divisor is a whole number, write the decimal point for the quotient above the decimal point of the dividend, and then simply divide as a whole number. And again, remind yourself that when dividing, be sure to not omit necessary placeholder zeros. That's a very common error. Let's also remind ourselves that fractions are divisions. This fraction bar is another way of saying divide. This reads 4 divided by 5. Now note, in this case we are dividing by a whole number. The decimal point of this whole number is always to the right, and our rule says if you're dividing by a whole number, the decimal point of the quotient is right above the decimal point of the dividend. And also remember, behind the decimal point on the end, you can insert as many zeros as you want. Now dividing, 5 goes into 4 0. 5 goes into 48. 8 5s is 40. So it quits. So 4/5, if we treat as a division, is equal to the decimal 8/10. Now that makes sense. See, in this case, if I were to multiply top and bottom by 2, I would indeed get 8/10, which is what this is saying. In particular, note when I divided this fraction, the decimal terminated. It quit. It came out even in the division. Sometimes that does not happen. Transforming this fraction into its division problem, reminding ourselves that the decimal point is on the end and that I may insert as many zeros as possible, and reminding ourselves that when I'm dividing by a whole number, the decimal point of the quotient is right above the decimal point of the dividend. Now dividing, 9 does not go in, well, it does go into 4 0 times. Then 9 goes into 40 4 times. 4 9s is 36, subtract, gives you 4, bring down the next. 9 into 4, 40 is 4 times again. And it doesn't take very much before you realize that we're in an unending looping situation. That in fact I'll keep on getting 40, 36, 40, 36, and this quotient will be 4, 4, 4, 4 forever. Now it's a fact that at some point the division of all fractions or whole numbers will either terminate or have some portion form an infinite repetition. That's a fact of fractions and whole numbers. An example, if I were to carry out that indicated division, I would reach a point where a portion, in this case the 1/7, begins to repeat forever. A growing notation in mathematics is this. Whenever that occurs, rather than going on forever or rounding off, very frequently we will write the quotient until we have at least passed the first repetition. And then we would show a bar over the portion which is to repeat. So if you saw a number like this in a technical book, that means either it has terminated here, which would give me 317 1,000ths, or else it has gone further and I have rounded off, but we don't know what is down the line. Whereas the bar is our way of saying the portion under the bar repeats forever. Watch for your books in the future and see how many are using that notation. It's a very convenient notation. But again, all fractions, at some parts, sometimes sooner, sometimes very late, will have some portion, small or large, begin to repeat. Now, back to the main topic, division by decimals. We now know how to divide a decimal by a whole number. But this one is not a whole number. So the procedure we will use is simply this. If the divisor is a decimal 2, move the decimal point until it reaches the end. However many places you moved it, move the decimal point in the dividend the same number of places. So that now we treat the decimal point as though it's here and not there. Now, it's as though we had rewritten the problem, and the problem is 17 divided into 39.1, as indeed it is. Now we are dividing by a whole number, so the decimal point of the quotient is directly above the decimal point of the dividend, and we simply divide. 17 into 3 is 0. 17 into 39 is twice. Now you can see I won't need that 0 since it's in front of the decimal point. 17 into 51 goes 3. In this case, it terminates. Again, move the decimal point to the right end. However many places you moved it, move the quotient, the dividend decimal point, to the right as many places. So what you're really doing is trading one problem with a decimal point to an equivalent problem with a whole number divisor. Once again for our notes and memory. If the divisor is not a whole number, move its decimal point to the right until it is a whole number. Then move the decimal point of the dividend the same number of places to its right. Then continue as you have in the past. Again, if you're not dividing by a whole number, move the decimal point to its right until it is a whole number. 2. Then move this decimal point to its right just as many places, in this case 3. If additional places are created, you use placeholder zeros. So my divisor has become 2, and my dividend has become 4180. Now the decimal point is here, goes straight up, and I divide. And I'm done. That's simple. Let's do another. In this case, they want us to stop and round our answer to the nearest thousandth. Let's see why. First, moving the decimal point to the right end. This one, the same number of places. Then the decimal point goes straight up. Then begin to divide by 29. And we would get 0 here, which I don't write, 0 here, which I don't write, and 4 here. Multiplying, we get 116. Subtract, we get 14. Now behind the decimal point, we can tack on as many zeros as we wish. So if I bring down the next 0 and divide in, I'll get another 4. 116. Subtract, we get 2, 4. Bring down the next 0. Now I know I'm going rather fast here, but I'm presuming that you could follow me on your own more slowly if necessary. Okay, now it goes into this 8. 8 times 29 is 232. Subtract gives me 8. Bring down the next 0 is 0. 29 goes into 80 twice. 58. Subtract 22. Bring down the next 0. 29 goes into 220 7 times. And as you might suspect, this is going to go on forever. I can't go until I quit. And it may be a long time before a portion repeats. So perhaps we're using this problem in a technological sense where if I have it accurate to the nearest thousandths, that's all the accuracy I can use on my instruments anyway. So in that case, which is usually the case in technology, we will tell you when we don't need any more because our instruments can't read it anyway. So you'll go out at least one place further. Now note that. Wherever we want you to round, go one place further, because that digit will tell us whether to round up or down. And since that's 5 or more, we round up, which makes that 3. So we can say 0.29 goes into 1.3, about 4.483, accurate to the nearest thousandth. And of course, such a problem is much more convenient on the calculator, where every number and operation and equal is a button. So 493 409.3 divided by 18.21 equals, and if I were to read my calculator, it's hard to see there, I have 2.707303679, depending upon how many digits a calculator allows for readout. Then repeat it very quickly. 49.3 divided by 18.21 equals, check yourself, always double check on calculators. It's easier to make a mistake on calculators than by hand, believe it or not. Now, we wish to round to the nearest thousandth. So there is tenth, hundredth, thousandth. We look at only the digit next to it. It's less than 5, so we round down, and that's my answer. Recall that when we were solving equations involving multiplications, we agreed that dividing undoes multiplication, and that we simply have to divide both sides of those equal expressions, and that gives us, in this case, x equals 7. The important thing here is division undid that multiplication, isolating the variable, which is what we call solving. Now, when we get to decimals, it's exactly the same thing. If you wish to undo that multiplication, we'll divide by whatever is doing the multiplying, but we'll divide both sides. And this division undid this multiplication, isolating my variable. Now this simply says 20.25 divided by 1.5. We would either do that by hand or by calculator, depending upon your situation. So 20.25 divided by 1.5 is 13.5. Now in that case it came out evenly. So my variable x is 13.5. So again, if you have an equation where the variable is being multiplied, you undo multiplication by division, by the thing that's doing the multiplying. And conversely, if your variable was being divided by a constant, we undid the division by multiplying. But then I have to multiply both sides. So in this case, the multiplication by 7 undoes division by 7, isolating the variable. And of course the other side is 77. So to undo dividing a variable by a constant, you multiply by a constant, and that isolates the variable. So it is with decimals, just messier arithmetic, that's all. So in this case, to undo this multiplication division by 1.7, I will multiply by 1.7 both sides. This multiplication undoes that division and has isolated my m. Now multiply either by hand, or if you wish, or are permitted to, by calculator. So 0.9 times 1.7 is 1.53. And I'm done. As a student, it's really better if you do the multiplication and divisions by hand and then check by calculator, and that way you are reviewing two things at once and really getting double your money for that course. Try it. It's really worth it. Let's give you an example of where those algebraic equations come from. It's a story problem. A rectangle is to have 40 square meters of area. Its width is 3.2 meters. What must be its length? Now actually the situation that brought this problem about was this. There were two buildings which happens to be 3.2 meters apart. A contractor wished to front in the building but it needed for its purposes an area before he put the back in, and the area for the purpose that was being used in this building site had to be 40 square meters. So our question is, how far back should he go? It's this common situation in architecture and drafting. Well, what we have here is a width, a length, which I don't know, and an area. So we ask ourselves, in a rectangle, what is a relationship between width, length, and area? And again, you recall from previous lessons, the area of rectangles is length times width. But in this case, we know what the area is to be. That's 40. It's the length that we don't know. And we know the width has to be 3.2. So we have restated our geometric and story problems in terms of an algebraic equation. Now, to find out what L is, we call in algebra solving for the variable. In this case, the variable is being multiplied by 3.2. So it's not the 3.2 we initially want to get rid of, it's the multiplication. So we recall that multiplication is undone by division, and naturally division by the same number. But the division law of equality says if I divide one side of the equation by anything, I must divide the other side by the same amount. So division undoes multiplication, isolating the variable, which is what I wanted to happen. So this says, look, L is 40 divided by 3.2. So 40 divided by 3.2, and if I didn't have the calculator, using the review furnished by this lesson, we move the decimal point to the end, giving me 32, but I have to move this decimal point one place the same direction. So I must remind myself that the decimal point is on the end, the right end of all whole numbers. If I move it one place to the right, I've created an extra place. So I insert a placeholder 0. Now that I'm dividing by a whole number, the decimal point of the answer is right above the decimal point in the dividend. Now we simply go through and divide. And we won't use your time here, but it does come out to be 12.5 meter. So we would tell the architect or draftsman, make this area 12.5 meters deep, and you will have the desired 40 square meters of area. This kind of situation occurs innumerable times in technology, drafting, landscaping, surveying, virtually every area that exists that uses numbers. One more example. In electricity and electronics, there is a common law called Ohm's law. It could be expressed algebraically in this formula, where R stands for something called resistance and is measured in a unit of measure called ohms, and E stands for electromotive force and is measured in a unit of measure called volts, and most people are familiar with that. And I is a measure of electrical current and is measured in a unit called amps. Now let's suppose in a given situation we know this. Let's say somehow you know that the resistance in a circuit is 3.8 ohms, whatever that is, and that's not important to the algebra of this situation. And you also knew that your current is 2.2 amps, but you don't have a device to measure the voltage, but right then and there you do need to know what the voltage is. Could you find it anyway? Well, in this case, we know the value to replace these two variables because our situation tells us that. So, let's do it. Up here, let's replace the r by its replacement value of 3.8. It's equal to the e, which I don't know, but the I do know is 2.2. Now what we have is an algebraic equation, and we wish to solve for e. And again, the whole emphasis of these many reviews we've been having is for you to concentrate first not on the number, but the operation between that number and the variable, which is division, and to ask yourself, what operation undoes division? And of course, by now, you should know it's times. And of course, times the same number. But the multiplication law of equalities is if I multiply the quantity on one side by anything, I am permitted to do that only if I multiply the quantity on the other side by the same amount. Now this multiplication undoes this division, which says that my E, the voltage, is that times that. So we simply use our knowledge of the previous lesson or calculator and do what our algebra is directing us, 2.2 times 3.8. And we have that the voltage must indeed be 8.36 volts. Now, there's a valuable lesson to be learned in these two problems, and that is this. If you know how to play the game of algebra, in fact, algebra tells you what to do to what numbers and when. Many beginning students often ask, what do I do? And if you play the game of algebra, indeed it tells you what to do. In this case, it tells me to undo division, I must multiply. Now it's telling me if I want the voltage, I will multiply these two numbers specifically. Again, these two problems might be a little bit strange to you, but as you pursue your career, whatever it is, you will find many problems. These come from electronics, from carpentry, from landscaping, from fisheries, from cooking, from baking, all of these areas. Each has their own specific formulas. And what we're saying here is if you know all of the values except one particular one, by playing the game, we can find what that particular one must be to satisfy our given physical situation. Really, quite simple. This is your host, Bob Fennell. We'll see you at the next lesson. Good luck.